Welcome to section 3.2, systems of linear equations in 3 variables. Okay, so we've moved up the amount of variables. So if we have 3 variables, in order to solve, we need 3 equations to solve. Just like if we have 1 variable, we need 1 equation to solve. If we have 2 variables, we need 2 equations to solve. So now we're moving into 3 variables, which means we're going to be looking at 3 equations and working with that type of a system. So as we looked at with 2x2s, when you're talking about 2 lines that were intersecting, that was what sort of the answer to a 2x2 system looked like. What might the solution to a 3x3 system look like? Well, there are actually a number of possibilities, and you can check that out in your book because there are more than I'm going to write down here. But one of the main possibilities is if you're thinking about your room. For example, if you're sitting in a room right now, take a look at the walls of your room and where they meet in a corner of your room, right? Let's say you're sitting in your room at your desk. Okay, so you look at that wall, the 2 walls, they meet at one point here, right? And then, if you also bring into account your ceiling, right? The ceiling that's above you, all of those places, the ceilings and the walls, they meet up at one point, right? The very corner tip of your room. So that would be one of the main ways we can think about the solution to a 3x3 system. We're looking at something that is in 3D, so your room, for example, is in 3D, and exactly where your walls and your roof meet, boop, that point would be the answer to a 3x3 system, which we would usually do with x, y, and we bring in a third variable, z. Z is new to the party. This is the third variable we're bringing in, because we're in 3D. Now, for example, that is one answer, but sometimes we don't have a solution, and that is because when we're talking about 3x3, we're talking about planes instead of lines. That's if you have, let's say if you imagine 3 pieces of paper floating above one another, they never intersect, so there would be no solution there. And then there's one other example. Once again, there are about 8 in the book. I'm only going to do 3 here. The other example is if all the planes that you have, and it's kind of hard to draw 3D, if they all intersect at one line, and I'll go ahead and draw like that. They intersect here. The book has a little better of a visual, but they intersect at a line. And since they're intersecting at a line, we can't just write our solution in this sort of x, y, z format. That would be where we would say infinitely many solutions, because it's a line, we can't write all those points out. So these are our visuals of the possibilities. We have 1 point, no points, and infinitely many points for planes, which is an equation with 3 variables. So let's take a look at steps for solving a 3x3 system. So the first step we're going to do, and these steps vary, they differ from the book a little bit. These are the steps that I use. So first thing is you're going to pair off the equations. But since there are 3 equations, you don't have even pairing, which means one will be used twice. And that is usually the simpler equation. Second thing we're going to do is we're going to choose to eliminate the same variable from each pair. Okay, and this is really, really important. This is where some students forget. It needs to be the same variable from each pair. Because once you've done that, then you'll get 2 equations in 2 variables. So now you'll pair the 2 new equations. Fourth step is you're going to solve the 2x2 system, which means you'll have 2 of your variables. Perhaps you might have solved for x and y, which means you're still missing z. So the next step you're going to do is go back to an original equation to solve for the missing variable. And lastly, final answer. If it's not a word problem, you'll just answer in x, y, z format. If it is a word problem, answer in a sentence. Okay, very basic. So usually the basic plan is to eliminate z from each variable, but that's really generic. It doesn't always work. So let's take a look at example 1. Solve the following system. Okay, so how do I know that this is a system, first off? Well, we have multiple equations, and we have that bracket right there. Next, we have 3 variables going on in our equations and 3 equations. So I know this is a 3 by 3. So what would my plan be? Well, something I like to do in the beginning before I do anything else is to make sure the equations look like they're simple. I notice in the first one, these are all divisible by 4. And then I notice in this bottom one here, those are decimals, and I don't want to work with the decimals. So I'm going to go ahead and first simplify my equations before I actually begin working with them. So I'm going to divide the top one. I'll divide them all by 4. Once again, simplify if you can. So it'll be x plus y plus z equals 2. Oh, that looks way better. The bottom one, or sorry, the middle one, doesn't look like I can simplify it, so I won't. And then the bottom one, let's see, what could I do to make that simpler? They're all, let's see, I'm going to rewrite this in terms of half. So that'll be negative half x plus 1y minus half z equals half. If I multiply this equation by 2, I can get rid of those fractions. So let's do that. Multiplying everything by 2, when I distribute that 2 into each of those terms, I get negative x plus 2y minus z equals 1. And let's write that down. Once again, it's important to use the braces bracket thing when you are working with the system. So make sure to include that. Alright, so now it is simplified. So now I'm going to go ahead and work on the first step for solving 3 by 3 systems, which is to pair them off. But as you recall, since there are only 3, one of them has to do double duty, and that should be the simplest one. So which one of these looks like the simplest equation? And that's kind of up to you, but I'll go ahead and use this one to be paired off twice. So I'll go ahead and write it down twice. And then I'll go ahead and rewrite each of the other ones with one of the pairings. So this one I'll put down here, x minus y plus 2z equals 2. And this one I'll put down here, negative x minus 2y minus z equals 1. Now, the plan is, once we've paired them off, we're going to decide to cancel one of the variables. So, I'm going to think, which one is easier to cancel? Well, looking at this, we have the x's and the x's here. They all have the exact same variable in front of them. You'll notice the y's here would be harder to cancel out because that one has a 2y, even though it would be easier to cancel here. So what I'm going to do is I'm going to cancel out the x's. So cancel the x's. And once again, we need to cancel it from both pairings. So how would I cancel the x's from the first group here? Since they're both positive x, I'm going to go ahead and use subtraction for all of this. So x minus x, that cancels out. We're done. And then we have y minus negative y. So it'll be y plus y, which would be 2y. And then we have z minus 2z. So z minus 2z is going to be a negative z equals. And lastly, for this one, we have 2 minus 2, which is 0. So there's my new equation. One equation in 2 variables. So now let's move on to the other one. In order to get rid of the x's, this time we'll actually have to add them together instead of subtract. Why? Well, x plus negative x, that'll give me 0x, so the x's are gone. Now we have y plus negative 2y. Well, that looks like it's going to be negative y. And then we have z plus negative z. Oh, what do you know? The z's also cancel. So we're left with just the y variable. And lastly, we have 2 plus 1, which is 3. And you know what? I'll just go ahead and solve for y here. Look at that. We have a bonus. We actually managed to find the answers to one of our variables in the first step. Okay, so that was the first thing. So the next thing we're going to do now is to pair the new equations. So pair new equations. So this should look familiar because this is going to be a 2 by 2 system. We have the 2y minus z equals 0 from above, and then the y equals 3. So now we have a 2 by 2 system, which we have worked with before. So to solve this, I could use elimination, I could use substitution, or I could graph. Graphing is not preferable, so I think I'm going to use substitution. I know y equals 3, so I'll just plug that into my equation here. So I have 2 times 3 minus z equals 0. Once again, I just rewrite my equation with 3 where y used to be. So then I have 6 minus z equals 0. I'll add z to both sides. And I get 6 equals z. Aha! We have found 2 of our variables. We're almost there. So now, to find the third variable, the missing variable, we can use either one of these equations. I'll go ahead and use that one right there. X plus y plus z equals 2. So I'll label this finding, which one are we missing? Finding x. So you're using x plus y plus z equals 2. Let me go ahead and check that I wrote that right. Yep, okay. So I have that 6 is equal to z, so I'll replace that with 6. And then I have that y equals 3. I'll replace that with 3. So solving for x, we have x plus 3 plus 6 equals 2. Then I get x plus 9 equals 2. Let's subtract 9 from both sides. And we get x equals, let's see, negative 7. Aha, we have found all of our variables. How do we answer? What is our final answer? Well, we have to do the x, y, z format. So my answer is going to be x, so negative 7, y is 3, and z is 6. And there's my solution. So let's take a look at example 2. Solve the following system. Alright, so let's see. Well, we have the 3 variables and we have the 3 equations. None of them look like they can be simplified, so I'm just going to go ahead and skip right into the pairing off step. But you'll notice this bottom equation here only has 2 variables. So my plan's going to change a little bit. I'm going to pair these guys off here. And I want to get rid of the variable that this one does not have. Alright, why would I do that? Because then I would get I would get 2 equations and 2 variables. So what variable is missing from that bottom equation? Well, it's missing z, which means my plan is to cancel out the z's. Okay, because if I cancel the z's, when I pair it up with that equation there, the 2y equals x, I'll have 2 equations and 2 variables. So let's go ahead and do that. In order to cancel the z's, this needs to become a 5z, which means I need to multiply everyone else by 5 as well. So multiplying 29 by 5, let's see what I get. 29 times 5, that is going to be 45, 10, 14, 145. Okay, and that'll be 145. Alright, so let's go ahead and I'm going to rewrite this to make it look a little nicer. And then we want to cancel our z's. Okay, so in order to cancel the z's, since they're both positives, I'm going to go ahead and use a negative. So 5x minus 3x, that's going to be 2x. 5y minus 4y, that'll be positive y. And then the 5z minus 5z, they'll be canceled. And they have 145 minus 105, so that'll be 40. And now we have our new second equation. We'll go ahead and plug that in right over here. And now we can solve a 2 by 2. So I already know that x equals 2y. So let's go ahead and solve this with substitution by replacing x with 2y. So solving with substitution, I get 2 times 2y plus y equals 40. So that'll be 4y plus y equals 40, and then we get 5y equals 40. Dividing by 5, we have that y equals 8. Okay, we found one of the variables. So how do we find the other one? Well, let's go ahead and we can use that equation right there to find the other one. Why would we not go back to one of the equations with the 3 variables? Well, if I just had one y, then I would still, if I plugged 8 in there, I still have an x and a z to solve for, and I can't solve for one of them if I only have one equation. So I'm going to go back to the simpler equation of 2y equals x, and I can solve for x. So let's go ahead and label that, solving for x. Once again, labeling is really important, especially when you're working with systems. So we have 2y equals x, and I know that y equals 8. So 2 times 8 equals x, 16 equals x. Awesome. So we found 2 of our variables. We just need to find the third one. Which equation do I choose? Well, it's up to you. But I'm going to go ahead and choose the top one. Why did I choose it? Well, it's simpler than the middle equation, and I'm trying to solve for z, which is why the bottom equation would not work for solving for z. It doesn't have a z. This one's too complicated, so I'll use that to solve. Let's go ahead and say solving for z. So I'm going to use, what was the equation? It was x plus y plus z equals 29. Alright, so my x is 16. My y is 8. And let's solve for z. So 16 plus 8 plus z equals 29. So 16 plus 8. Let's see, what is 16 plus 8? So that's 14 and 14, so 24. Minus 29 from both sides. Sorry, minus 24 from both sides. And then z equals, well, 29 minus 24 is going to be 5. So what would my answer be? It's not a word problem, so we'll just answer in the coordinate set. So x first, 16. Y next, 8. Z next, 5. Once again, the order is important. It's x, y, and z. So just think alphabetically. Alright, that is it for this section. If you have any questions, please drop by in office hour.